Right now, beyond Neptune's orbit, dozens of space rocks are moving in patterns that defy explanation unless an unseen massive planet is controlling them. These trans-Neptunian objects orbit with surprising alignment, suggesting something substantial is influencing their paths. This represents the compelling scientific case for Planet 9, a world 5 to 10 times more massive than Earth hiding in the outer solar system. The mathematics suggests it exists, but finding it has become astronomy's greatest treasure hunt, like searching for a ghost ship in the cosmic ocean that leaves only ripples as evidence. This orbital puzzle has astronomers scanning the skies, piecing together clues what could be our solar system's most elusive member. The orbital puzzle. What if the map of our solar system is missing its most massive piece? A piece so significant that it fundamentally changes our understanding of our cosmic neighborhood? This isn't a hypothetical question. It's a serious scientific possibility based on mathematical evidence and strange orbital patterns observed at the edge of our solar system. When astronomers look beyond Neptune, they find a population of frozen worlds called trans-Neptunian objects, or TNOs. These are essentially icy bodies orbiting the sun at extreme distances, much farther out than the 8 recognized planets. The Kuiper Belt, which begins just beyond Neptune at about 30 astronomical units from the sun. $1 Australian is the Earth-Sun distance, contains thousands of these objects. Based on our understanding of how solar systems form, these TNOs should orbit the sun with random orientations. Their orbital paths should point all different directions, like spokes on a wheel when viewed from above, similar to how the numbers on a clock face extend in all directions. But that's not what astronomers found. In 2014, astronomers Chad Trujillo and Scott Shepard noticed something strange. The most distant TNOs, those wandering far beyond Neptune's gravitational influence, weren't behaving as expected. Instead of random orbital orientations, these objects showed a peculiar clustering. Their orbits were aligned in a way that shouldn't happen by chance. The perihelions of these distant objects were clustered together in space, and their orbital planes were tilted in similar ways. This observation became even more significant when astronomers Konstantin Batygin and Mike Brown at Caltech analyzed additional objects and confirmed this pattern in 2016. They found that TNOs with orbits longer than 4,000 years showed this strange alignment. The odds of this happening randomly? Less than 0.007%. In other words, this clustering pattern would occur by chance only once in about 14,000 solar systems. Take the strange case of Sedna, one of the largest known TNOs. Discovered in 2003, Sedna follows an extremely elongated orbit that takes it from about 76 Australian dollars at its closest approach to the Sun out to nearly 1,000 Australian dollars at its farthest, well beyond the Kuiper Belt. Objects like 2012 VP13, nicknamed Biden, follow similarly unusual paths. These discoveries provided crucial early evidence in a pattern that Batygin and Brown would later analyze in detail. What makes these alignments particularly puzzling is that these objects never come close enough to Neptune to be influenced by its gravity. They're too distant to be explained by any known planet's gravitational pull. Yet something is organizing them, something massive enough to herd these distant worlds into similar orbital patterns over billions of years. Here's what the data show. These distant TNOs have orbits that are both physically clustered and oriented in similar directions. When astronomers plot the orbital parameters, they find that the arguments of perihelion cluster around 0 degrees. The longitudes of perihelion also cluster together rather than being randomly distributed around 360 degrees as expected. Furthermore, these objects share another strange characteristic. They all have highly inclined orbits that tilt in the same direction. This is particularly strange since objects so far apart shouldn't know about each other's orbital orientations. It would be like finding that cars in different cities across the country were all parked at the same angle. There must be some reason for such coordination. When astronomers create simulations comparing the expected distribution versus what's actually observed, the contrast is striking. What we see is a distinct clumping in particular regions of space, as if these distant objects are being shepherded by an unseen force. What could possibly be organizing these distant worlds? The mathematical answer that emerged, a massive planet, much larger than Earth but smaller than Neptune, orbiting the Sun at an extreme distance in the outer solar system. This hypothetical planet would need to be on an elongated orbit inclined to the plane of the solar system to create the observed patterns. Its gravity would gradually shepherd these smaller objects into their aligned orbits over billions of years. The statistical significance of this clustering, 3.8 sigma, indicates it's highly unlikely to be coincidental, compelling enough for serious scientific investigation, though not yet meeting the gold standard discovery. With this compelling orbital evidence, astronomers began developing a hypothesis to explain this cosmic mystery. They started running computer simulations to determine what kind of planet could create these exact orbital patterns, testing different masses, distances, and orbital characteristics. Through mathematical modeling, researchers at Caltech determined that a planet about 5 to 10 times Earth's mass on an orbit tilts about 30 degrees to the plane of TNO clustering. This planet would take between 10,000 to 20,000 years to complete a single orbit around the Sun. The simulations showed that over billions of years, this planet's gravity would gradually force TNOs into the exact orbital patterns we observe today. The orbital puzzle of these distant objects had yielded an extraordinary possibility. Our solar system might contain a ninth major planet that has escaped detection until now. But how could astronomers prove the existence of a planet they couldn't directly see? The answer lay in the same approach that led to Neptune's discovery in the 19th century, through its gravitational effects on other objects. The hunt for Planet 9 had begun, using invisible influence as the primary clue to its existence. Invisible influence? How do you prove something exists when you can't see it? This isn't just a philosophical question, it's a practical challenge that astronomers face when searching for objects at the edges of our solar system. For Planet 9, the evidence doesn't come from direct images, but from the invisible pull it exerts on other bodies. This approach has a long and successful history in astronomy. When we look at those clustered TNO orbits, they tell us something profound. A massive gravitational influence is shaping them. Despite extensive searches of the outer solar system, telescopes haven't captured any images of a large planet that could be responsible. This invisible influence presents both a puzzle and an opportunity. By studying the affected orbits of smaller objects, astronomers can mathematically reconstruct what remains hidden from view. Detection through gravitational effects rather than direct observation has proven reliable in astronomy's history. In 1846, astronomers noticed Uranus wasn't following its expected orbit due to an unknown gravitational pull. Two mathematicians, Urbain Le Verrier and John Couch Adams, independently calculated where this unknown planet would need to be. Their mathematical predictions led directly to Neptune's discovery, pinpointing a world that had remained invisible until calculations revealed exactly where to look. Today, this same mathematical approach drives the Planet 9 investigation. When Konstantin Batygin and Mike Brown examined distant trans-Neptunian objects, they discovered something statistically improbable. The 6 most distant known objects all followed elliptical orbits pointing in the same direction in physical space. The odds against this happening randomly were overwhelming. Something had to be organizing these orbits, and the most plausible explanation was the gravitational pull of a substantial unseen object. Initial calculations suggested this object would need to be quite massive, a true planet with several times Earth's mass. Smaller objects simply wouldn't exert enough gravitational force to shepherd these distant worlds into their observed patterns. To test this hypothesis, astronomers employed powerful computer simulations that function like virtual solar systems. These tools allowed researchers to introduce different types of planets and observe how their gravity affects smaller objects over billions of years. By comparing simulation results with actual observations, they could determine which scenario best matched reality. After testing numerous configurations with planets of different masses and orbits, a specific solution emerged. The data pointed to a planet with 5 to 10 times Earth's mass, orbiting at an average distance of 500 to 600 times the Earth-Sun distance. This orbit would be highly elliptical, taking the planet between about 200 and 1,200 astronomical units from the Sun. Crucially, the planet would follow an anti-aligned orbit, its closest approach to the Sun occurring 180 degrees across from the perihelions of the aligned TNOs. This anti-aligned orbit is central to the Planet 9 hypothesis. Simulations showed this configuration prevents smaller TNOs from colliding with the massive planet while keeping them aligned through mean motion resonance, similar to how Neptune maintains Pluto in a stable orbit, though operating over much greater distances. The simulations revealed Planet 9 would naturally produce objects like Sedna by gradually pulling standard Kuiper belt objects into more extreme orbits less influenced by Neptune. This explained puzzling discoveries of objects with highly elliptical orbits too distant to be affected by Neptune's gravity. What makes these mathematical models compelling is their consistency. Simulations of a solar system without Planet 9 strongly contradicted the observed data. The probability that the observed clustering was merely coincidental was calculated to be less than 1/100%. As Badigan and Brown noted, a solar system without the hidden planet is strongly refuted by the data. The model also predicted additional effects that have since been confirmed. For instance, it predicted objects with orbits perpendicular to the plane of the solar system, and such objects have indeed been discovered since the hypothesis was first published. Each matching discovery strengthens the mathematical case. These calculations provide astronomers with search parameters. Based on the predicted orbit and mass, they can estimate Planet 9's brightness, sky motion, and likely position. While these estimates cover a substantial area of sky, they significantly narrow the search compared to blindly scanning the entire outer solar system. The proposed mass of 5 to 10 times Earth's would make Planet 9 the 5th largest planet in our system, smaller than gas giants, but substantially larger than Earth. This size plays in the category of super-Earths or mini-Neptunes, a common planet type found around other stars, but absent in our solar system until now, perhaps. The mass suggests this missing planet would reshape our understanding of the solar system's architecture. While mathematics can't reveal everything about this world, it provides a framework for what telescopes should seek in their ongoing search for our solar system's most elusive member. The cosmic detective story. What are these space rocks telling us that we've missed for centuries? Throughout the outer solar system, a group of unusual objects are silently providing evidence that could rewrite our understanding of planetary science. These distant trans-Neptunian objects serve as silent witnesses in our cosmic detective story, celestial bodies with particular orbital characteristics that challenge our current model of the solar system. They communicate through their paths, telling a coherent story despite being separated by billions of miles. The key testimony begins with Sedna, discovered in 2003. This planetoid follows an extremely elongated orbit, traveling from about 76 astronomical units at its closest approach to the Sun, perihelion, to an astonishing 1,000 Australian dollars at its most distant point, aphelion. For perspective, Earth orbits at 1 Australian dollars, while Neptune orbits at about 30 Australian dollars. Sedna's journey around the Sun takes approximately 11,400 years to complete. Sedna's orbit reveals something extraordinary. It never comes close enough to Neptune to be influenced by the ice giant's gravity. While most objects in the outer solar system have their orbits shaped by Neptune's gravitational pull, Sedna exists in a detached state, seemingly beyond the influence of known planets. The plot thickened in 2012 when astronomers discovered another object with remarkably similar characteristics. Designated 2012 VP-113, nicknamed Biden, this object's closest approach to the Sun occurs at about 80 Australian dollars, even more distant than Sedna, and it too remains beyond Neptune's gravitational reach. Both objects inhabit what scientists consider a dead zone, where the known planets exert minimal gravitational influence. Their elongated orbits carry them far beyond Neptune, with the majority of their journey spent in the distant frigid regions where our solar system transitions to interstellar space. As astronomers identified more distant objects, a compelling pattern emerged. Objects like 2015 TG-387, nicknamed the Goblin, and 2015 BP-519 displayed orbital characteristics aligning with Sedna, and 2012 VP-113. These extreme TNOs share detached, highly elliptical orbits with suspicious similarities, like multiple witnesses independently corroborating the same account. The most revealing aspect of these orbits is their clustering. When mapped, their elliptical paths point the same direction in physical space. Their perihelions, closest approaches to the Sun, occur in the same region rather than being randomly distributed. This alignment sparks wonder among astronomers. It's as though these mute cosmic travelers are collectively pointing towards something unseen. Even more telling, these objects' orbits tilt approximately 30 degrees downward in the same direction relative to the plane of the 8 known planets. Calculations place the probability of this alignment occurring randomly at about 0.007%, virtually ruling out coincidence. The clustering extends to the argument of perihelion, a technical parameter describing where an object's orbit makes its closest solar approach. For these distant objects, these values cluster around 0 degrees, another pattern that shouldn't occur by chance. Orbital resonance might explain some outer solar system objects, but these extreme TNOs don't match known resonance patterns with Neptune or any other known planet. While Pluto orbits the Sun exactly 3 times for every 2 Neptune orbits, creating a stable relationship, Sedna and its companions show no such resonances with any known planet. Observing these objects over thousands of years would reveal them tracing massive elongated paths, never approaching Neptune or other giants. Yet somehow these widely separated objects share orbital characteristics suggesting a common influence, a shared storyteller affecting their cosmic journeys. The mathematical improbability of this happening randomly about 1 in 100 has compelled astronomers to consider alternative explanations. These TNOs function like buoys in the cosmic ocean, aligned by an underwater current, responding to an unseen force organizing their movements. The most plausible explanation is the gravitational pull of a substantial planet-sized world at the system's edge. Over billions of years, this planet's gravity would gradually shape the orbits of smaller passing objects, herding them into similar patterns. While glacially slow by human standards, this process works perfectly on astronomical timescales. The trans-Neptunian objects reveal a significant gap in our understanding, suggesting a massive planet shepherds their movements from beyond our current observational reach. The patterns in their orbits represent fingerprints left by an invisible hand, one belonging to a planet we've yet to directly observe. Based on its gravitational effects, astronomers can estimate this potential Planet 9's likely size, mass, and composition, painting a picture of a substantial world that would reshape our understanding of the solar system's architecture. A giant in hiding. Just how massive would a planet need to be to command the outer solar system? To shepherd distant trans-Neptunian objects into their suspicious orbital patterns, this hypothetical planet would need substantial gravitational influence, far beyond what a small object like Pluto could exert. Based on the observed orbital clustering, astronomers have calculated specific physical characteristics for Planet 9, painting a portrait of a substantial world lurking in the darkness. The scientific estimates of Planet 9's physical characteristics start with its mass, the primary factor determining its gravitational influence. According to the mathematical models developed by Battigan and Brown, Planet 9 would need to be between 5 and 10 times more massive than Earth to produce the observed orbital alignments. This estimate comes from complex calculations analyzing how much gravitational force would be required to herd those distant objects into their current clustered patterns over billions of years. This mass range makes Planet 9 a cosmic heavyweight, substantial enough to command the outer reaches where it resides. With 5 to 10 Earth masses, it would dwarf all 4 inner planets combined while remaining smaller than our gas giants like Jupiter, 318 Earth masses, and Saturn, 95 Earth masses. Planet 9 would occupy the middle ground between terrestrial planets and ice giants, falling into a category astronomers call super-Earth, or mini-Neptune. The significance of this classification extends beyond our solar system. Super-Earths and mini-Neptunes are among the most common planets discovered around other stars, yet our solar system appeared to lack any examples in this size category. Planet 9 would fill this curious gap, potentially making our planetary neighborhood more typical rather than an outlier among stellar systems. Based on its estimated mass, astronomers calculate Planet 9's radius at approximately 2 to 4 times Earth's, about 12,700 to 25,500 kilometers across. This would rank it as the 5th largest planet in our system, smaller than Neptune, but significantly larger than Earth. Like a sleeping giant amid cosmic shadows, this substantial world has enough gravitational pull to reshape the distant solar system while remaining hidden from our view. A planet of this size would possess sufficient gravity to maintain a substantial atmosphere. While direct observations remain elusive, astronomers theorize its composition based on comparable objects. Most likely, Planet 9 has a rocky core surrounded by thick layers of ice and gas, similar to Uranus and Neptune, but with different proportions depending on its formation history. The planet's composition would vary based on where it formed. If it originated in its current distant orbit, it would contain a higher proportion of ices, water, methane, ammonia, and other compounds that remain solid at extremely low temperatures. If ejected from a closer orbit, it might have a more substantial rocky core with a thinner layer of volatiles. Either way, it would likely maintain an atmosphere containing hydrogen and helium, though less abundantly than Jupiter or Saturn. One of Planet 9's most extreme characteristics would be its temperature. At hundreds of times Earth's distance from the Sun, Its surface temperature could plunge to about minus 226 degrees Celsius, minus 375 degrees Fahrenheit. In these frigid conditions, gases we consider atmospheric on Earth would freeze solid, creating a surface blanketed in exotic ices. This extreme cold would likely make Planet 9 remarkably dark, reflecting minimal sunlight. Its low reflectivity combined with vast distance creates perfect conditions for concealment despite its substantial size, a massive world effectively camouflaged by darkness and distance. The presence of such a large planet in the outer solar system challenges current planetary formation models. Standard theories expect rocky planets near the star and gas giants farther out, but not necessarily super-Earths at hundreds of times the Earth-Sun distance. Confirmation of Planet 9 would prompt reconsideration of formation theories. The planet's origin remains equally puzzling. Did it form in its current distant orbit, or was it once closer to the Sun before being ejected outward? Perhaps it wasn't born in our solar system at all, but was captured from another star system during a close stellar encounter billions of years ago. Each scenario would result in different compositional characteristics, making discovery even more scientifically valuable. So how big would Planet 9 be compared to Earth? The calculations suggest 5 to 10 times Earth's mass and 2 to 4 times its radius, a substantial world with enough gravitational influence to shape the outer solar system over billions of years. This leads to the most perplexing question. Where could something so massive remain hidden? How could a planet larger than Earth escape detection despite our advanced telescopes and sky surveys? The answer lies in the vast scale of the outer solar system. Planet 9's potential hiding place encompasses an almost unimaginably huge region.
The cosmic hiding place. Where in our vast solar system could something so massive remain unseen? The answer lies in the extraordinary scale of space beyond Neptune. The visible solar system that appears in textbook diagrams, the 8 planets from Mercury to Neptune, represents only a tiny fraction of the Sun's gravitational domain. Beyond Neptune stretches a region so vast and dimly lit that even large objects can hide effectively from our telescopes. Planet 9's predicted orbit places it hundreds of times farther from the Sun than Earth. While Earth orbits at a comfortable 93 million miles from the Sun, 1 astronomical unit or AU, and Neptune circles at about $30 AUD, Planet 9 would orbit at an average distance between 400 and 800 Australian dollars. At 700 Australian dollars, Planet 9 would be approximately 65 billion miles from the Sun, a distance so enormous that light itself, traveling at 186,000 miles per second, would take over 4 days to reach the planet from the Sun. To grasp this immense scale, consider that the entire orbit of Neptune, which defines what most people consider the edge of the planetary solar system, would appear as a small circle when viewed against Planet 9's vast orbital path. If Neptune's orbit were represented by a large pizza, Planet 9's orbit would extend well beyond the boundaries of an entire football field. The orbital calculations for Planet 9 reveal its extreme distance and several other distinguishing characteristics. The mathematical models suggest an orbit with significant eccentricity, meaning it's highly elliptical rather than nearly circular like most planets. While Earth's orbit is almost a perfect circle, Planet 9 would follow an elongated path that takes it from about 200 Australian dollars at its closest approach to the Sun, perihelion, out to approximately 1,200 Australian dollars at its most distant point, aphelion. This elongated orbit creates substantial detection challenges. The planet spends most of its time at the farthest parts of its orbit, where it moves slower and is hardest to see. At these distances, Planet 9 would be approximately 1,000 times fainter than Pluto as seen from Earth, reflecting minimal sunlight back toward us. Adding to the concealment, Planet 9's orbit is significantly tilted. The models suggest an inclination of about 30 degrees relative to the plane of the solar system. This means Planet 9 travels on a different plane than the other planets, requiring astronomers to search not just far from the Sun, but also above and below the main planetary plane. Together, these 3 orbital characteristics, extreme distance, high eccentricity, and significant tilt, create the perfect cosmic hiding place. Planet 9 exists in a region where the Sun appears merely as a bright star, providing minimal illumination. The little light that does reach Planet 9 must then travel all the way back to Earth before we can detect it, resulting in an extremely faint signal. The planet's motion further compounds the detection difficulty. At 700 Australian dollars, it would shift by only about 3 arc minutes per year, roughly 1/10 the diameter of the full moon. This glacial pace makes it difficult to distinguish from background stars, requiring observations spaced months or years apart. With an orbital period between 10,000 and 20,000 Earth years, Planet 9 completes less than 1/millionth of its orbit in a human lifetime. Over decades of observation, it would appear to move in almost a straight line rather than showing noticeable curvature in its path. These factors combine to create an astronomical needle in a haystack problem. The search area spans hundreds of square degrees of sky, equivalent to searching an area hundreds of times larger than the full moon. Within this enormous region, astronomers must detect a tiny point of light moving almost imperceptibly among thousands of background stars and galaxies. Planet 9 likely resides in what astronomers sometimes call the inner Oort cloud, or distant scattered disk, a transitional region between the Kuiper belt and the hypothesized Oort cloud. This frontier extends far beyond where most spacecraft have ventured. Even the Voyager probes, which have left the solar system after traveling for over 40 years, have only reached about 125 Australian dollars and 105 Australian dollars respectively, still much closer to the Sun than Planet 9's predicted orbit. The vastness of Planet 9's orbital domain, combined with its faintness and slow movement, creates the perfect hiding place for a substantial world. Despite being potentially larger than Earth, it remains hidden in the darkness of space, challenging our current observational capabilities. Finding such a distant, dim, slow-moving object presents immense technological challenges. The hunt for Planet 9 requires sophisticated detection methods and powerful telescopes capable of piercing the darkness of the outer solar system, technologies that are just now becoming available to astronomers in their quest to unveil this mysterious world. The hunt begins. What technology could possibly spot a world hiding in the darkest reaches of our solar system? Finding Planet 9 presents one of the greatest observational challenges in modern astronomy. Despite being potentially several times larger than Earth, this hypothetical planet remains hidden due to its extreme distance and the minimal sunlight it reflects back to Earth. Conventional telescopes face significant limitations when searching for Planet 9. At 400 to 800 astronomical units from the Sun, any reflected sunlight would be approximately 100 million times dimmer than Neptune, while its slow motion makes it difficult to distinguish from stationary stars and galaxies. Add to this the vast search area, hundreds of square degrees of sky to examine, and you have what amounts to an interstellar game of hide and seek, where the hider has chosen the darkest corner of our cosmic backyard. Could this elusive world be hiding in plain sight, already captured in our astronomical data, but not yet recognized? This question drives astronomers to develop specialized techniques for their hunt. One approach involves multi-year sky surveys that systematically photograph large areas of the night sky repeatedly over time. By comparing images taken months or years apart, astronomers can identify objects that have moved slightly, a signature characteristic of distant solar system objects rather than stars or galaxies. These surveys generate massive amounts of data requiring sophisticated computer algorithms to process. These algorithms detect extremely subtle position changes while filtering out instrument errors, cosmic rays, and other artifacts. Today's high-performance computing makes this possible, allowing astronomers to sift through terabytes of image data looking for that one moving pixel that might represent Planet 9. While visible light searches continue, infrared astronomy offers another promising avenue. Planet 9 retains internal heat from its formation and from the decay of radioactive elements in its core. This heat radiates as infrared energy that specialized telescopes can detect, making the planet appear brighter in infrared compared to its extremely faint visible light reflection. The Infrared Astronomy Satellite, IRIS, and the Japanese Aerospace Exploration Agency's Akari satellite have provided valuable data for this search. These space-based infrared telescopes performed all sky surveys that might have captured Planet 9, even though they weren't specifically looking for it at the time. A study led by astronomer Terry Long Fan of the National Tsinghua University in Taiwan demonstrates this approach's potential. Fan's team analyzed data from both IRAS and Akari, looking for objects that appeared in the IRAS database and showed movement when observed by Akari 23 years later. The perfect time separation for identifying slow-moving distant objects like Planet 9. The team searched for objects that moved between 42 and 69.6 arc minutes over that 23-year period, the expected motion range for a planet at Planet 9's predicted distance. This methodical approach filtered out millions of static objects, focusing only on potential candidates showing the right movement over time. Remarkably, Fan's team identified a single object as a strong Planet 9 candidate. This object appeared in one position in the IRAS image and was detected by Akari in a slightly different position 23 years later. The movement matched what would be expected from a distant planet orbiting the Sun. However, with only 2 data points, the team couldn't determine the object's full orbit to confirm its planetary nature. Meanwhile, some of the world's largest telescopes have joined the hunt. The Subaru telescope, an 8.2-meter optical infrared telescope on Mauna Kea in Hawaii, has conducted dedicated Planet 9 searches. Its large mirror and wide field of view make it particularly well suited for this search. The telescope's Hypersum Prime can capture an area of sky equivalent to 7 full moons in a single exposure, efficiently searching large areas where Planet 9 might be hiding. Other facilities contributing include the dark energy camera on the Victor M. Blanco telescope in Chile. This camera's extremely wide field of view makes it excellent for survey work and follow-up observations of potential Planet 9 candidates. The technology used represents astronomical observations cutting edge. Modern telescope detectors can register individual photons, making them thousands of times more sensitive than photographic plates used just decades ago. Computer systems can analyze billions of pixels of image data, identifying moving objects that human eyes might never notice. Despite these impressive technological capabilities, the search remains challenging. Planet 9's extreme distance, faintness, and slow motion test the limits of even our most advanced instruments. However, astronomers remain optimistic. Historical precedent suggests that mathematical predictions of unseen planets can lead to successful discoveries, just as calculations by Adams and Leverrier led to Neptune's discovery in 1846. The most promising developments lie in the near future, with next-generation instruments set to begin operations in coming years, potentially bringing Planet 9 from mathematical hypothesis to confirmed discovery. The Vera Rubin Game Changer. Could a revolutionary new telescope finally solve astronomy's greatest modern mystery? While current searches for Planet 9 face significant limitations, a next-generation observatory scheduled to begin operations in late 2025 promises to transform our ability to detect distant solar system objects. The Vera C. Rubin Observatory, currently under construction in Chile, represents what many astronomers consider our best chance, yet to either confirm or refute the Planet 9 hypothesis. Astronomy has historically been transformed by new observational capabilities. Just as Galileo's telescope revealed Jupiter's moons and Hubble unveiled distant galaxies, a remarkable new observatory may soon resolve one of modern astronomy's most compelling mysteries. Located on Cerro Pachón in northern Chile, this facility offers ideal viewing conditions with clear skies, high altitude, and excellent access to the southern celestial hemisphere, where much of Planet 9's predicted orbit likely resides. The Rubin Observatory represents a fundamental leap forward in our capacity to search for faint, slow-moving objects. 3 revolutionary capabilities combine to create an observing system perfectly suited for finding objects exactly like the hypothesized Planet 9. First, its 8.4-meter primary mirror gathers substantial light from extremely distant objects. This meticulously polished mirror concentrates faint light, with its collecting area directly correlating with the ability to detect dim objects. Second, its 3.2 gigapixel camera, the largest digital camera ever constructed for astronomy, captures images with extraordinary detail and sensitivity. This massive LSST camera can detect a golf ball from about 15 miles away and holds 40 full moons in a single exposure. The camera's focal plane contains 189 individual CCD sensors, creating an effective imaging area 40 times larger than the full moon. Third, the observatory employs an innovative observing strategy called the Legacy Survey of Space and Time, LSST. This approach systematically photographs the entire visible southern sky every few nights. Over its planned 10-year operational period, the telescope will visit each portion of the sky approximately 825 times. This repeated coverage creates a time-lapse of the night sky, allowing astronomers to identify objects that change position. Each image is stacked and compared with previous ones, making it possible to detect extremely faint objects invisible in single exposures. For the Planet 9 search, this strategy automatically identifies anything moving relative to background stars. The LSST survey will catalog an estimated 37 billion stars and galaxies. Among these, it will likely detect millions of solar system objects, including approximately 100,000 new trans-Neptunian objects. This expanded census will provide more evidence of Planet 9's gravitational influence and might directly image the planet itself. Scott Shepard, staff scientist at the Carnegie Institution for Science, whose work contributed to the Planet 9 hypothesis, has expressed remarkable confidence in the Rubin Observatory's capabilities. According to Shepard, the observatory has a 70 to 80% chance of finding Planet 9 if it exists. This high probability stems from the observatory's combination of sensitivity to faint objects and comprehensive sky coverage. For a cautious scientist like Shepard to suggest that such a high probability indicates real confidence in the observatory's capabilities. The observatory's software systems match its impressive hardware. Sophisticated algorithms will analyze the massive data stream, automatically flagging objects showing the telltale motion of distant solar system bodies. The system will generate approximately 10 million alerts per night for objects that change brightness or position, with specialized filters designed to identify the slow movement expected from a distant planet. This automated processing addresses one of the greatest challenges in the Planet 9 search, distinguishing a slowly moving planet from millions of background stars and galaxies. Processing about 20 terabytes of data nightly, the specialized software will identify the most promising candidates for follow-up observation. The Rubin Observatory will also help resolve whether the observed clustering of trans-Neptunian objects is statistically significant or results from observational bias. By systematically surveying the entire sky, rather than focusing on limited regions, the observatory will establish whether the apparent patterns in TNO orbits persist in a larger, more uniform sample. What will the Vera C. Rubin Observatory reveal about Planet 9 starting in 2025? It could finally confirm or rule out Planet 9's existence. If Planet 9 exists within the parameters scientists have calculated, the observatory has a strong chance of finding it during its 10-year survey mission. Equally important, if the observatory doesn't detect Planet 9, that absence would indicate that alternative explanations for the observed orbital clustering deserve more serious consideration. The fact that we're just a few years away from potentially resolving this major scientific question highlights how scientific progress often depends on technological advancement. The Planet 9 hypothesis emerged from careful analysis of existing data, but its confirmation requires new observational capabilities that are only now becoming available. Origins of a ghost planet. How could such a massive planet end up so far from the Sun? This is the puzzling question that emerges when considering Planet 9's unusual location. If confirmed, this world would orbit hundreds of times farther from the Sun than Earth, a region where substantial planets aren't expected to form according to our current understanding of solar system development. The standard model of planetary formation tells us that planets form from the protoplanetary disk, a rotating disk of gas and dust that surrounds a young star. In this model, the densest part of the disk is closer to the star, allowing more material to accumulate and form planets more quickly. This explains why we find the largest planets in our solar system, Jupiter and Saturn, in the middle regions, while smaller worlds tend to form closer to the Sun where less material was available. Planet 9 would break this pattern completely. At hundreds of astronomical units from the Sun, the protoplanetary disk would have been extremely thin, containing far too little material to form a planet several times more massive than Earth. This fundamental contradiction forces astronomers to consider alternative explanations, each telling a dramatic story about our solar system's history. Imagine cosmic billiard balls careening through space, distant stars passing like ships in the night, or isolated pockets of creation in the cold outer reaches of our solar nebula. These vivid scenarios represent the three competing theories for Planet 9's unusual position, each with profound implications for how we understand planetary system evolution. The first theory suggests that Planet 9 formed much closer to the Sun, in the same region where the gas and ice giants developed, but was later ejected outward by gravitational interactions. In the early solar system, the giant planets likely occupied different orbits than they do today. They migrated from their formation locations in what might have been a chaotic cosmic dance. During this turbulent period, Jupiter and Saturn, the solar system's heavyweights, exerted tremendous gravitational influence on smaller worlds. Computer simulations showed these giants could have flung a substantial planet outward like a cosmic slingshot. If Planet 9 originally formed as another ice giant near Uranus and Neptune, a close encounter with Jupiter or Saturn could have launched it into a highly elongated orbit reaching far beyond the known planets. This ejection scenario aligns with evidence of a dynamic early solar system. The current arrangement of planets and smaller bodies suggests significant rearrangement occurred during the first 100 million years. Objects like Sedna already indicate that substantial gravitational disturbances shaped the outer solar system. Planet 9 could represent the most dramatic example of this planetary reshuffling. Yet, ejection isn't the only possibility. The second theory proposes something seemingly impossible. Planet 9 actually formed where we now expect to find it, in the distant outer solar system. While challenging conventional models, unique circumstances might have allowed a substantial planet to develop at such extreme distances. Perhaps the solar nebula was unusually extended, providing enough material even at great distances. Alternatively, density enhancement in particular regions might have created local concentrations where planet formation became possible despite the generally low density. This formation in place scenario would require extremely efficient accretion over long timescales, as potential building blocks would encounter each other less frequently than in the inner solar system. If both these explanations seem unlikely, there's a third possibility that ventures into even more dramatic territory. Planet 9 might be an immigrant to our solar system. Instead of forming here, it could be a captured planet that originally orbited a different star. Stellar encounters were common when our sun was young, especially if it formed in a dense cluster, alongside many other stars. During a close passage with another star system, the sun's gravity could have stolen a planet from the passing star. Computer simulations show that such captures, while rare for any specific encounter, become plausible when considering the many stellar encounters that likely occurred during the sun's first few million years. A captured planet would typically end up in precisely the type of distant, elongated orbit that scientists predict for Planet 9. Computer models have tested all three scenarios extensively. The ejection scenario works well in about 10% of simulations that include an additional ice giant in the early solar system. Capture simulations suggest it would occur in less than 10% of stellar encounters, but given many such encounters in the sun's youth, the overall probability remains significant. The formation in place scenario faces the most challenges, requiring specific conditions to overcome limited material resources. Whatever its origin, Planet 9 would force a significant revision of our understanding of planetary system formation. The mechanisms that placed such a massive world at these extreme distances would reveal processes that shaped not just our solar system, but potentially planetary systems throughout the galaxy. As we refine our search for this elusive world, we're simultaneously exploring the fundamental processes
Rewriting
that
the
create
solar
and
system
sculpt
story.
planetary
What if
systems.
everything we thought we knew about our cosmic neighborhood is incomplete?
The discovery of Planet 9 wouldn't just add another dot to our solar system map. It would fundamentally change our understanding of how planetary systems form and evolve. Our current models of solar system formation follow a relatively orderly process. A cloud of gas and dust collapses, forming a star surrounded by a rotating disk. Within this disk, solid particles stick together, gradually building up larger objects until planets emerge. This explains the current arrangement: rocky planets close to the sun, gas giants in the middle regions, and smaller icy worlds beyond. Planet 9 breaks this neat model. Its estimated mass, 5 to 10 times that of Earth, and its extreme distance from the sun challenge our current understanding. Material hundreds of astronomical units from the sun would be far too sparse to form such a substantial world through standard accretion. The protoplanetary disk at that distance simply contains insufficient mass to build a planet several times larger than Earth within our solar system's lifetime. This contradiction forces astronomers to reconsider fundamental aspects of solar system formation. If Planet 9 formed in its current position, traditional theories need significant revision. If it formed elsewhere and moved to its current orbit, our understanding of planetary migration must expand to account for more dramatic orbital changes than previously thought. A super-Earth in the outer solar system would resolve a puzzling discrepancy between our system and others. Astronomers studying other planetary systems find super-Earths and mini-Neptunes. Planets larger than Earth but smaller than Neptune are extraordinarily common. Roughly 30% of Sun-like stars host planets of this size range in close orbits. Yet our solar system appears to lack planets in this mass category. This absence has raised questions about what made our solar system different. Was there something unusual about the Sun's protoplanetary disk? Did Jupiter's formation prevent super-Earths from forming or surviving here? Planet 9 would provide a missing piece. Our solar system would have a super-Earth after all, just in an unexpected location. Planet 9 would offer new insights into the early chaotic period of our solar system. The standard model suggests that giant planets didn't form in their current locations, but migrated significantly. Jupiter likely moved inward, then outward again, while Uranus and Neptune were pushed outward by gravitational interactions with larger planets. During this migration period, substantial gravitational interactions could have ejected some planets from original orbits. If Planet 9 formed closer to the Sun and was later flung outward by Jupiter or Saturn, it would represent the most dramatic example of this chaotic rearrangement. Its existence would confirm that the early solar system experienced significant restructuring. Beyond explaining trans-Neptunian orbital patterns, Planet 9 could help resolve other mysteries. It might explain Sedna-like objects with highly elliptical orbits that never bring them close enough to Neptune to feel its gravitational influence. Planet 9 could naturally produce these objects by gradually pulling standard Kuiper belt objects into more distant orbits. It might also explain the surprising discovery of objects in the Kuiper belt with orbits inclined almost perpendicular to the plane of the planets. These highly inclined orbits are difficult to explain with known planets, but simulations show a planet with characteristics similar to Planet 9 could produce such extreme tilts over billions of years. The planet's existence would connect to theories about stellar encounters in the Sun's youth. When the Sun formed, it was likely part of a star cluster where other stars passed relatively close. If Planet 9 was captured from another star system during such an encounter, it would provide direct evidence of these early stellar interactions. Finding Planet 9 would suggest a more complex, dynamic picture of planetary system formation. Rather than planets forming and largely staying in place, it would point to a history where substantial worlds can be flung to new orbits or captured from other stars. This aligns with growing evidence from exoplanet studies that planetary systems frequently experience significant restructuring. The discovery would also raise questions about how common similar planets might be in the outer regions of other systems. If our system contains such a world, similar planets might exist in the outer reaches of other planetary systems currently undetectable with our technology. How would finding Planet 9 change our understanding of solar system formation? It would require rewriting our solar system's history, suggesting a more dynamic, chaotic formation process, and potentially explaining why our planetary system differs from many others we observe. Our solar system would emerge as a more actively sculpted system that experienced substantial rearrangement during its development, reshaping our understanding of planetary system architecture more broadly. The Skeptics Case. What if we're chasing a ghost that doesn't exist? For all the mathematical elegance of the Planet 9 hypothesis, a substantial portion of the scientific community remains unconvinced. These skeptics aren't simply being contrarian. They're applying the same rigorous standards of evidence that form the foundation of all scientific progress. Their alternative explanations for the observed orbital patterns highlight how the same data can lead to very different conclusions. Scientific skepticism serves as a crucial counterbalance to any new hypothesis, especially one with such far-reaching implications. The Planet 9 debate represents science at its best, a continuous process of questioning, testing, and refining our understanding rather than rushing to embrace exciting but potentially premature conclusions. One of the most significant challenges to the Planet 9 hypothesis comes from concerns about observational bias. Renu Malhotra, a Regents Professor of Planetary Sciences at the University of Arizona, argues that the apparent clustering of TNO orbits might be an artifact of our limited view of the outer solar system. The problem stems from fundamental limitations in our observational capabilities. Astronomers can only detect the brightest TNOs when they're relatively close to the Sun, creating a systematic bias in our sample. We're essentially studying wildlife by only observing animals that visit a particular watering hole during daylight hours, missing the broader distribution patterns that might exist. This bias becomes particularly problematic when studying objects with highly elliptical orbits. We're most likely to discover these objects near their perihelion, their closest approach to the Sun, when they're brightest. What looks like the influence of Planet 9 could instead be a consequence of where and when our observations have taken place. If astronomers were able to observe the entire sky with equal sensitivity over longer periods, the apparent clustering might disappear entirely. Another alternative explanation challenges the need for a single massive planet. Some researchers suggest that the observed orbital patterns could result from the collective gravitational influence of many smaller objects. While individually these exert minimal gravitational pull, their combined influence over billions of years might create patterns similar to what we observe. This collective gravity hypothesis would explain the apparent clustering without requiring an undiscovered super-Earth. This theory gains credibility considering the Kuiper Belt and regions beyond remain largely unmapped. We've likely discovered only a small fraction of the objects that exist there, whose distribution and masses could significantly influence regional dynamics in ways our current models don't account for. Perhaps the most exotic alternative involves a primordial black hole. This hypothesis suggests that a small black hole created in the earliest moments after the Big Bang might be responsible for the observed gravitational effects. While speculative, a primordial black hole with roughly 5 to 10 Earth masses would be physically tiny, about the size of an apple, yet exert exactly the kind of gravitational influence attributed to Planet 9. Beyond specific alternatives, some researchers question whether the observed clustering is statistically significant at all. Scott Shepard, whose 2014 study helped inspire the Planet 9 research, contextualizes these limitations. By now, we expected to have found many more of these extreme trans-Neptunian objects. Having several tens of objects would allow scientists to reliably determine if they are truly clustered in space. Right now, I would say it's possible there is a super-Earth planet in the distant solar system, but we cannot say that with a lot of confidence. The current sample of extreme TNOs remains small enough that chance alignments could create the appearance of patterns where none actually exist. As more objects are discovered, the statistical case for Planet 9 will either strengthen or weaken. The scientific conversation around Planet 9 illustrates what's at stake. The potential discovery of a new planet would represent a monumental scientific achievement. Malhotra observes that there is a perception that the idea of a Neptune-mass Planet 9 is being pushed more aggressively than the statistics justify. This tension drives research forward, with proponents and skeptics alike working to gather more data and refine their models. Could the evidence for Planet 9 actually be pointing to something else entirely? The viable alternatives, observational bias, collective gravity of many small objects, or even a primordial black hole, remain plausible given our limited data on the outer solar system. This healthy scientific skepticism doesn't mean the Planet 9 hypothesis is wrong, merely that it requires more evidence before widespread acceptance. The ongoing debate pushes astronomers to gather more data, improve their models, and consider alternative explanations, driving scientific progress forward. While professional astronomers debate the mathematics and observational evidence, the search for Planet 9 has expanded beyond professional observatories. Citizen scientists, everyday people with an interest in astronomy, have joined the hunt, bringing fresh eyes and unprecedented computing power to the search for this elusive world. The citizen planet hunters. Could the person who discovers Planet 9 be sitting at home right now? This question might seem far-fetched, but it's entirely possible. The search for our solar system's most elusive planet has expanded beyond observatory domes and university research departments to include thousands of amateur astronomers and space enthusiasts around the world. Professional astronomers face a fundamental challenge when searching for distant objects like Planet 9. Modern sky surveys generate staggering amounts of data, far more than the relatively small community of professional scientists can analyze effectively. The Infrared Astronomical Satellite, ARISS, mission, and NASA's Wide Field Infrared Survey Explorer, WISE, have captured millions of images covering the entire sky, potentially containing several pictures of Planet 9. Identifying a slowly moving dot among billions of stars and galaxies requires more eyes than astronomy departments can provide. This data overload created an opportunity for public participation in cutting-edge science. Astronomers developed platforms allowing anyone with an internet connection to join the hunt, leveraging humanity's remarkable pattern recognition abilities. While computers excel at processing data, the human eye outperforms machines at detecting subtle patterns within complex images. Backyard Worlds, Planet 9, launched in 2017, stands at the forefront of this search. The project invites volunteers to examine infrared images from NASA's WISE mission, which scanned the entire sky multiple times between 2010 and 2021. WISE operated at infrared wavelengths, making it ideal for detecting faint, cool objects like Planet 9. Participants examined sets of 4 infrared images taken at different times, looking for objects that shift position while stars remain fixed. A simple but effective approach that transforms ordinary citizens into potential discoverers of worlds. "We have too many images for our small team to search through by ourselves," explains the project description. The platform provides a user-friendly interface to help volunteers distinguish celestial objects from image artifacts like cosmic rays or satellite trails. The public response has transformed astronomical research. Thousands of volunteers have participated, collectively reviewing millions of infrared images. Participants range from astronomy enthusiasts with backyard telescopes to people with no prior scientific background, creating a vast network of searchers combing through data that would otherwise remain unexamined for years. These citizen scientists have achieved remarkable results. While Planet 9 remains undiscovered, volunteers have found numerous brown dwarfs, objects more massive than planets, but not massive enough to ignite like stars. Bob Fletcher identified a pair of brown dwarfs that had escaped detection despite their proximity to our solar system. Melina Thibonaut from Germany discovered a white dwarf hidden in the WISE images. Each discovery demonstrates how fresh eyes can spot objects that automated systems and professionals miss. The collaboration between professionals and amateurs creates powerful synergy. When citizen scientists flag potential objects of interest, professional astronomers follow up with more powerful telescopes to confirm discoveries. This division of labor allows professionals to focus their limited telescope time on promising candidates rather than the initial search phase. The partnership has proven so effective that professional astronomers struggle to keep pace with the interesting objects identified by volunteers. The project's success demonstrates how science advances when it embraces broader participation, combining professional expertise with the collective attention of thousands of volunteers. Some projects even invite amateur astronomers to make direct observations using their own telescopes. While Planet 9 would likely be too faint for most amateur equipment, the collective data from thousands of backyard telescopes could potentially yield results. What makes these initiatives particularly exciting is the democratization of discovery. The person who first identifies Planet 9 might be a professional astronomer, but they could just as easily be a teacher, accountant, or student reviewing images in their spare time. This unprecedented access to frontier science means the next significant finding in our solar system might come from someone with no formal scientific training. Participation also brings educational benefits. Volunteers learn about astronomy, data analysis, and the scientific process through direct involvement. Many report deeper understanding and appreciation for astronomy through their contributions. This citizen science approach represents a fundamental shift in how astronomical discoveries happen. Throughout history, major findings came from professional scientists with access to the most powerful instruments. Today, the limiting factor isn't necessarily telescope power, but human attention, the ability to examine mountains of data. By distributing this task across thousands of volunteers, modern astronomy creates discovery opportunities that transcend traditional academic boundaries. Whether Planet 9 is eventually found by a professional or a citizen scientist, the collaboration between these groups has already advanced our understanding of the outer solar system. The hunt continues, with thousands of participants examining images, looking for that one moving dot that might represent our solar system's most distant major planet. The search itself represents something profound, our collective human curiosity about the universe and our place in it. Planet 9 has engaged thousands of everyday people in cutting-edge science, reminding us that astronomical discovery belongs to anyone willing to look carefully at the night sky. The hunt for Planet 9 represents the frontier of modern astronomy, a place where mathematics suggests something our telescopes haven't yet confirmed. This search, regardless of outcome, advances our understanding of the solar system's architecture and history through improved observational techniques and mathematical models. As Melina Rice of Yale University explains, it could completely reshape our understanding of the solar system and of other planetary systems and how we fit into that context. Will the coming years reveal a ghost planet lurking beyond Neptune, or will we need to revolutionize our understanding of gravity itself? The answers await in the darkness,